Hey, welcome back to the bench. Good to see you again. Thanks for joining the channel. Hope you're all well. So today on the bench I got something really unique, and I think it's going to be a challenge, a real challenge for me. Decided it's been sitting here for about a year. I bought this thing at a flea market, and before I even got it home I didn't realize what it was. Now it's got its issues and it's going to need some work. This is a Technics stereo integrated DC amplifier, SU-V707. I think they made the 707 and they made another model. I don't know, was it 808 or 909 or something. It was a higher model, more power. This one's actually not too bad for power. I think it's 70 watts. I'm not sure. Don't quote me on that. I don't know. But it's got some nice features. Techniques integrated amp. Now excuse the dirt. So power switch, chunk power switch, and bass and treble controls. Okay. Then we have a operation of straight through DC coupled, or it's via the tone buttons, so we can push that in if we want to have tone compensation. Otherwise we go straight in. It has two lamps here, one for standby and one for power on. It has speaker selector, main and remote, and main and remote, so you got a choice of two sets of speakers. Record selector, okay, two sets of dubbing tape loops. Input selector, they have the tape monitors wired in with the input selector, so you can select your tape 1, tape 2, phono tuner, or auxiliary CD video. This is, I don't think this has any video connections on the back. It has a subsonic filter for phono, a loudness, and a muting. Then it has moving magnet, moving coil selector for your phono stage, a bounce control with cobwebs on it. Excuse the dust. And then here we have computer drive monitor, and it's got a little display of different lamps. It's got ICQ, and it's got a preheat and auto. It's got bias, high, mid, low. It has sensor, thermal, or signal. So I guess these are kind of a protection thing here. I'm not really quite sure. I'd have to read up on the manual about this, and it says computer drive new class A. So we know it's going to sound good, we hope. Let me turn it around and I'll show you what's wrong with this thing. So on the back panel they have quite a bit of this cut out for ventilation. So this is probably using a fair amount of power, getting a little warm, so they want the extra cooling. So we got inputs for audio, CD, video, one tape loop, two tape loops, our phono, which is moving magnet and moving coil, a tuner, and a graphic EQ extension, or it's in and out. Now I didn't see any controls in the front for this. This might be hardwired in and there's no way to switch it in and out. I think that's the case. So if you want to put something in here, you break the loop, you break the chain, put your device in. Actually they got these set wrong. Oh no, they don't, they're right. Got right channel to right channel. That's right. So yeah, if you want to break out something and add in here, you can. And then we have our two sets of speakers, and then here, I don't know if you noticed, we have no courtesy outlets. Why is that? Well, look at this. 50, 60 hertz, 510 watts, 220 volt. So this is a European unit, I don't know if you haven't guessed already. So it runs off 220. We need to figure out a way to make this work in North America on 125, 120. And crusty. I never did like these. Oh, very crusty feel to them. Okay, so yeah, that's one of the biggest hurdles we have right now. Is this is a 220 volt unit, and came from Europe. Is that Germany? Fresh and Nürburg? Furnish Nürburg? I can't pronounce German. Wonder if they're still around. Looks like they're a TV repair shop. Okay, so we need to figure out how we're going to get this converted. So let's do that. Alright, cover comes off. Looks not too bad. So what do we got here? We've got Power input here. This is all mains wiring. Looks like they have some chokes here, fuse, and some bypass caps. Big transformer. A couple of large caps here. They are 15,000 at 63 volts. So you know this is going to do the business. But we also have another problem here. We got a blown up channel, and somebody removed the devices from one of the channels. And I think I saw some other burnt parts in here. I'm not remembering. But they have the heat pipe arrangement. They have 4 devices sitting on this aluminum plate. Aluminum plate's coupled to this heat pipe. Heat pipe transfers heat out over to this side, which radiates all the heat. And power supply here. This is our bridge rectifier. This looks like some kind of, this is the computer drive board, they call it. And it's soldered down to the other main board. This one might be doing all the sensing of the amplifier, I'm not sure. And then this looks like input section, voltage amplification section. Oh, we've got a couple of blowed up transistors here. There's one. This one looks like it might be a driver, but who knows. There's one beside, it's got a big crack in the middle of it. So that one's shot too. There's some other parts burnt. Here is a diode that's kind of vaporized and missing. Another diode that's something wrong with it. So yeah, we got a lot of carnage going on around here. I think this is driver circuitry, I'm not sure. So at the back here we have an input board, and it looks like it's driven with these cables, the switching. We switch from the front panel, it goes back to these switches. These are actually switches here, and that does all our input switching. Looks like we have a tone board underneath here, and then we have a relay here. This is our speaker. Yeah, that's our speaker switch and our protection relay, and everything's on this board. And it does have a 2/3 removable bottom. So let's pull this off, have a look. Okay, the bottom off, you can see we have access to all of the main board bottom. Here's our missing devices here. And they cut out a big section for air to get through this radiator. The bottom of the tone board, switching board, whatever you want to call it. And that's about it. So there's no heavy damage. I don't see any damage to this board. No burn traces, no cooked board. So it's looking pretty good under here. I don't know. So I don't know if you agree with me or not, but this thing has some good bones to it. It's got, you know, it's got a lot of good features. It's got some good power behind it, and it's in a nice package. I really like this amplifier if it was a working amplifier. Apparently this amplifier was never released in North America. It was a European one only. But I could be wrong on that. I'm sure people will correct me. But we don't get these in North America. So this is kind of a rare beast. Now normally what I would do in a situation like this is just yank out this power transformer and replace it with something. I got mountains of power transformers here that I've yanked out of old receivers and AV receivers. Something that has suitable voltage, suitable current, and it will fit right in there, and then connect it up Bob's your uncle. But this is not your typical amplifier design. Now we have a little problem here because we have many taps on the outputs, different voltage taps, and we can't just slap another transformer in with a single voltage supply and have it work. Let's go have a look at the schematic. So one of the unique features of this amplifier is, aside from it's computer controlled, is it has automatic speaker impedance detection. Now what that means is it has this circuit, and what it does, I don't know if I don't know how, I didn't read through it or how it works, but I have an assumption. What it does is it takes a measurement of your speaker output. Where is it? But in essence, what this does is it senses the speaker impedance through this comparator, and then it sets up the logic, and then it either switches the transformer to a high voltage tap or a low voltage tap. High voltage, low current, low voltage, high current. So this transformer has special taps for impedance matching of the output speakers, kind of similar to what Harman Kardon does with their, but they have a switch instead of this complicated relay switching circuit, which is all automatic. So I just can't take this transformer out and replace it with something else because we don't have the proper taps on the secondary for the high and low, and this circuit is going to want to sense the speakers and set up the amp accordingly. But there is some hope because this might work. So this is the input power, goes in, power switch, that little board with the 2 chokes on it I was looking at. They're not shown here. This is a different version because I do not have the voltage selector tap. That is not available on mine. And I want to see if we have two primaries wired in series, or if we have just one secondary. If we have two primaries wired in series, then we can rearrange the wiring of the transformer, and we can feed it with 120 volts, and then we're off to town. We can do it. If this is just a single 220 volt winding, we're going to have to get a little more complicated on this and do something different, because we need to maintain these 2 taps. Here we have AC 34 volts on these 2, and then on these 2 outer ones we have 42 volts, or 42.5 volts AC on these 2. And then we have a, I think it says 9.5 volts auxiliary winding. So just can't find a transformer like that anywhere. Alright, here's the power transformer. Removed it. Have a good look at this. Now I think how this works is, this is our center tap, and then we have our 2 outputs for low voltage, high current, and then we have 2 more voltage taps for higher voltage, lower current, and then we have our auxiliary winding here. We have very thin wire on this one. So these are all our secondaries. And if we look on the other side, we get our primary, and from the looks of this, we only have 1 set of wires coming out. So this is a 220 volt tap on this, and it's unfortunate we can't just rewire this to make it work on 120 volts. So we got thermal fuse, goes in, thermal fuse comes out, connects to the one winding, and then the other winding comes out. So what I propose to do, and it's going to sound a little crazy, but I think I'm going to try rewinding the primary on this to adapt it to 120 volts. And never done that before, but I think it's possible. Let's try it. So let's see how we're going to do this. Let's open this thing up. Let me see. This is going to be fun. We need to get this thing out of the holder and separate it from the core. Wow, this is going to be fun. Okay, I got to start on it. Let's just straighten these tabs out. This should work. I'm gonna have to straighten this all out after anyway. Okay, we should have enough time to get it out. There we go. All right, remove this. And if it all falls apart, maybe I will find one out of a Harman Kardon. I don't know. We'll see how this goes first. I have a feeling this might just work. And we'll be in luck. We can just remove the core and the winding and just rewind it. All right. I think we're in luck because we have an EI core, but they're not interlocked, they're welded. So what they have is they all have all the E pieces here, and then they have the I pieces here, and then they made a weld, and they made a weld. So I just need to go take the grinder and grind out this weld, right here, and grind out this weld, and the top will come right off, and that'll expose the inner core, and the windings can come right out. So let me go to the garage, I'll grind this off, and I'll be right back. There we go. Alright, we're in. We'll save that. We'll be welding that back on top. So, who's that? And then we can get our core out now. What I'm going to do is I'm going to tap the core out, and we'll work on the windings. I should have removed this before. I'll have to put that back on later. Okay, keep that. And then we can take the core out. Okay, here it is, separate from the core. This is our iron core. We're going to keep that and reuse it. Here's our windings. Now this can come apart. It has a couple of insulators on here. Take these off for now. And I don't know if you can see this, but there's the outside core winding. These are the secondary, and then the inside winding is your primary. We can separate these two just like this. But first I need to disconnect some wires because this is going to all rip apart if I don't do it properly. So I got to remove these wires. Probably got to remove this end piece because it's clipped on both sides here. And then we can take out the center, the primary winding. Alright, back at the bench. Let's remove these wires. Just got to peel them off the post. Okay. Okay, so that wire has our thermal fuse on it too, and then this one has just a thermal fuse. I don't know what they're using for thermal fuse, probably 100 and maybe 95C or something, who knows. We'll find out when we get in. Just going to remove this one as well because it'll just end up getting broken. Okay. All right, let's bend these back. Let's see if we can ease this apart. There we go. There we go. Yes, it's working. Okay, now we can push this out. And there's our primary winding with our thermal fuse. All right. It's a little crusty, but we can rewind this. And let me just take some pictures and stuff so I don't forget things. And then we'll get started on rewinding this. Now you're probably wondering how I do the math and I'll figure out all the calculations for wire size and all that. Well, I'm not going to do any of that. What I'm going to do is I'm going to unwind the original wire, and then I'm going to fold it in half to double it up, and then I'm going to wind it right back on. So that should, in theory, put half the turns that it already has, so from 220 volts down to 110 volts. And it should double the current capability of the wires themselves. Let me bust up this thing. This is going to be tough, all this stuff here. So I could count the number of turns, or I could just actually what I'm going to do is I'm just going to put it onto another reel and count the turns as I take them off, and then I'll have to figure out a way to fold this wire in half and wind it back on without getting it all kinked up and knotted. So that's going to be my goal for today, and hopefully we can get this thing back in service. I have to clean this stuff off though. I don't want to damage any wires. I think once I get the first wrap off, it's going to be all clean. Alright, so I'll get ready for that. I'll get a reel of some kind to roll it onto, and then we'll work on it from there. Okay, I'm back, but this is a fail. This, I don't have it wound properly. This is not going to fit back in. It has to go in from this side. No, it has to go from this side. This side? I forget already. But this is no good. But I do have it doubled up. So what I could do is I could unwind it and rewind it slowly, carefully. The problem is the varnish that they put on this is like shards of glass, and it slices my hands up. So I think now that I've gone through the worst part, I can unwind this onto a reel and then take my time, make sure it's spaced properly and laid down properly, and we should be able to get this no problem. It's just going to take a little time. So I'm going to rewind this and we'll get it back together. Don't worry. Okay, it's going slow here, but it's actually going not bad. One thing I found that helps is every time I do a layer, I lay down some tape along off the corner. See the tape here and tape here? And that allows me a nice surface to see where the wire needs to lay, and I don't overlap on the corners. And I just go through and I just lay down layer after layer, and then I'll put another layer of tape on the corners after I'm done this layer. And I just go through and keep it nice and tight. It's probably a machine that does this in 5 seconds and just zip and then it's all on, but we're just doing it the old-fashioned way. And I think this is going to be the biggest hurdle for this amplifier. I think if we can get this power transformer thing sorted, we're going to have a good base for putting together a nice power amplifier. It's got some nice features and it's got some nice specs, I think. And we're going to make it sing again. But this is pretty tedious. I'm just going to go through, sit and watch a YouTube video or listen to music, and I'll do this and I'll get it finished. I'm just finishing up the third layer now. And see this stuff here? This is like, it cuts you open like glass. That's the part that gets me. And now that I actually unwound it and rewinding it the second time, it's a lot cleaner and I don't have all those shards. It seems like they all came off. So I'm going to finish this layer and then we'll lay down some tape. Even this corner doesn't look that great. Just tighten it up. Yeah, you can tighten it up too, see? And I'll just... Alright, I won't bore you with this. Alright. Second time around went a lot better. Still have some width to get rid of here, but took my time and carefully, sort of carefully, didn't always get it 100%, but got it layered out. Tried not to get twists in it, and but I think it's going to work. Okay, so let's see how this fits. Might have to I think it's going to work. I just got to squeak it in. You know what I'm going to do? I think I'm going to get some tape on here to help keep it protected when I slide it in. Yeah, it should go in. Let me tape it up. You put too much tape on, you're just making it thicker. I just want to protect the wiring. Okay. Before I get too carried away, this is the thermal fuse. Now I had a little look at this, did a little bit of reading. It says I can't see it. 250 volt, 169 degrees Celsius, and it is 10 amps. So that can go drop right in here. Put these wires down so they don't break. We got to get this thing in. So I might have to use some trickery, like a credit card or something, to help it. Oh, yeah, I'll get some credit card and I'll just use it as a wedge. Wow, that was tight. So what I had to do is I had to take an X-Acto knife and shave the inside corner here, give it a beveled edge, and I did that on both sides, well, 3 sides, and that helps it go in. It's just about home, and I'm just pushing it in. I need something thinner now. Just about there, but it fits, and there it is. It's in. Now if it's going to work another third, that's another story. Oh, I have to do that fuse first. I want to take this piece out. I can just drop the fuse right into this socket. And then it'll be protected from the windings because it's in a little pocket. There's no chance of it shorting out. Okay, I'll get that. Get this to click in. Maybe, maybe not. There we go. That side clicked in. Now I'm going to have to crush this down to get it to fit in the core. I think it's going to fit the core fine. It's going to be a tight squeeze, but we'll get it. Okay. Okay, it's the next day. My hands are all sliced up from working with that wire, and give them a couple days for my hands to heal. But I think we're at a point where we can put this back together. Now, in hindsight, it probably would have been better if I just took off all that wire, threw it in the recycling bin, and started with new wire with a thicker diameter. But I would have to calculate how many turns, what gauge of wire, how, you know, all that business. How, you know, and I don't have the ability to do that. I don't have the smarts. I know some people do, but I don't. But this is why I went the way I did. But in hindsight, if you're going to do this, don't try and rewind the same wire, because it didn't work out that great. But we got it together. Now the trick is to get this back together, and we have to fit this in here somehow. And it doesn't look like it's going to fit. Like, it looks like These are swollen now. These are definitely swollen, but they are compressible, so I might have to get something on there to compress that. And we need to put this back together. So first step is to clean the surface of any foreign matter that's gonna cause the gap to be bigger than it needs to be. We clean this off. All the old varnish. Clean off. I think that's okay. A little bit here. Now if I can get this core back on, we can weld it back together. Now, doing this is a big risk because I might have a shorted winding, which would render this totally useless and garbage. The chances of a shorted winding, though, are pretty slim rate at this point, I don't think. Another trick is going to be, how do we weld this? I'm going to put everything back together and clamp it in a vise, and then I'll just run a bead. That's not the right side, is it? Is it this side? This side. Yeah. I should mark that, actually. Doesn't really matter, as long as it goes back together and we have minimal gap. We don't want any gap here. We want full conduction of magnetic field. These were on here. We'll put these back on. That's going to protect us when we put this back into the core. I don't want to make it any thicker than I have to. Okay, so let's see if I can get this back together. Okay, I got it half on. It's starting to go. What I did is I took a file and I cleaned up these inside edges because they were quite sharp and jagged. And all these four inside edges here, I just gave a file and just put a little slight 45 bevel on them just to knock off the sharp edges. And it allows it to go in without digging into the plastic. That's what's helping me out here. It's just a matter of pushing it on. I might need some extra weight or a press maybe, but it is going to go. Just got to get it back on. This side here is quite pushed out. I don't know why, but it should all compress and go back in. So let me fight with this. Okay, I did manage to get it in. A little persuasion with some wooden block and a hammer type stuff, and I made sure that I was protecting the wires as it went in. It still has to go a little bit. This is proud, maybe a millimeter or so, so I'm going to have to get this to bottom out and seat, and then we can get this welded back on, because right now I have a gap. I think I can probably clamp it in a vise, something like this, and squeeze the crap out of it, and then do my weld. Let's see. Yeah, it's not. Probably need a C-clamp here. Clamp that and then we'll weld it. Okay, I'm back after a little sparky, grindy. This is all, just put tape on here to protect the windings from sparks. Now, you can see that I welded up. Not as good as factory because I'm not a machine. I can't weld like a machine. I got poor hands, coordination, eye coordination, and this will work. Now before I step any farther, I think we should test this. We should connect some AC to this and see what's going on inside. If we have any problems, we'll detect it now, and then we can just abandon this instead of doing any more work. But yeah, this should be okay. So I sputtered on some metal and ground it down just to, I had it clamped in a vise. So our gap is pretty good. You can see there is no gap really. So that's what you want. So let's get, let's see here. Let's get my Widowmaker. This is my Widowmaker. Plug on one end, clips on the other, and we're going to attach this to the primary. We're going to start feeding in voltage, AC voltage with the variac, and we're going to watch the current. If we have a shorted turn, this will turn up. Put a red flag for us right now. Now also, I think we should monitor the output a bit. So let's monitor the output. Where do we want to monitor? I think between these two. This would be our high voltage winding. Okay. We're all ready to go. Turning on the variac. Is it going to smoke? Got it at full voltage. And we have no excessive current. That's full voltage right there. We're putting in probably about 140 volts AC. So that's good. Now let's see what our consumption is open field. Watts, 13.5 watts. Now you got to remember, I rewired this from 220 to 110. So this is now a 110 volt transformer, and I'm feeding in 124. That's why we're getting a little funny, wonky numbers. That's why we're getting almost 100 volts on our high winding for the secondary. I'm just going to leave this on for a while and see if it does any weird heating up. Or 14 watts seems a little high, and it might be because of my welding. It could be a lot of things, but so far I think this is a success. So I'm just going to leave this powered up for a while, probably at line voltage, and just see what it does. Here's a look at the auxiliary winding, 11 volts. And then for the low B+, I'm going to measure it right now. It should be around 70 volts. What's going on with my meter? I won't measure it. Why won't this measure? Okay, this is 12 volts. There we go. Some weird stuff with my meter. Okay, yeah, 40 volts. And I think 78. Okay, so that was the center tap. Good. I think we're going to be in business here. Yeah, it's still kind of warm from my welding and my grinding, so where we're getting here about 35 degrees Celsius. I'm just going to let this cook for a while and see if it gains temperature or if it cools off. Here's an old transformer out of an old Sony. Just for comparison, I'm going to move these clip leads over to this primary, and I want to see what our consumption is on this core. And we got about 10.5 watts opened. So our core is probably not as efficient as this core because we did the opening up and re-welding it, and that might have messed up the laminations a bit in some of the spots. That's probably why we're getting an extra 3 or so watts of consumption from this transformer to this transformer. Otherwise, I think we're good. I think we're golden. So I'm going to continue with assembly of this one. Now this might be a bit tricky here. Let's see what we can do with this. Okay. What I want to do is add some solder to this. So let's heat up my iron. Okay, what I want to do is just add a little bit, not much, just to help with. Okay. Now, I don't know if I can do this with the iron or not. I'm going to try. Good way to burn my fingers. Okay, hang on. Let's clamp this somehow. I wonder if I can use this as a clamp. Put this underneath. There we go. Just gonna clamp this. Make it tight. Okay. Screwdriver and a torch. All right. Not the prettiest thing. What is catching here? Looks like we have lots of layers. And seated. Okay. This side here. I might need more vice action or clamps. It was a little bit of a struggle. I had to pry it in with the screwdriver, and then I got it. Finally got it. I can. So yeah, we are done. That is good. It's like I bought one. Okay, put that back in. We can start working on the rest of the carnage in that amplifier. Okay, I'm just going through and making a list of all the transistors I need for replacing all these blown parts, and we've got quite a mess here. We got this transistor, this thermistor is cracked as well, and it reads different than its neighbor. I don't even know if it's the same part because it looks different. It's thicker. We got diode blown. I think this resistor here is open. These two transistors are shorted. There's probably pre-drivers. We got a lot of stuff wrong in this area. I gotta go through. So what I'm gonna do is probably remove the heat sink and heat pipe just to get it out of here, because it's covering a lot of the printed circuit board back here. Back here, I'm gonna have to do some work back here too. I got all these caps and stuff. There's a relay under there that needs servicing. I'm going to redoing all the caps. Now another thing I need to pay attention to is supply voltages. Now that we got our transformer rewound, actually what I did is I rewound it to work on 110 volts, but I'm feeding it 125, so that's about a 12 or 15% over voltage condition for this amplifier. So I have to make sure that all of the supply voltages and other voltages are going to fall within reason as far as capacitors go, because we don't want to blow up any capacitors with over voltage. And any of these transistors have to be checked for voltage rating to make sure that they're going to work, because we're going to be boosting the supply voltages here. I'm trying to get a fix on what it says. I think it says right here 47.1 on low and 57.5 on high. And if we add 12 or 15% to that, that's going to go up considerably, probably closer to 65 or 63. And these caps are rated for 63. So we might have to upsize these caps in voltage, and probably a lot of other caps too, just so that we don't run into any troubles. So I'm going to remove the heatsink. I'm going to remove this computer drive board because it's kind of in the way too, and I want to service that separately. The main board we'll deal with last. Down here I got all the switches I need to clean. This is the input boards, and I have down here more caps. Everything's going to get recapped, but let's first try and get this thing. You know what? Let's try and fix this so it's working, and then we'll start worrying about recapping. But first I want to take the amplifier and disconnect it from the power supply so that we can install our transformer. It's still out. I can install the transformer, power this up, measure some voltages, and see what we're working with. And that'll be our starting point. And then from there we'll decide what we're going to do. If we're going to just fix this or if we have to start upgrading parts. So it's going to be quite a project, I think. I know. I like taking on challenges, but this one's a real challenge. And got to remember, all the work I did with this is all experimental. We don't even know if this is going to fly or fry. So we're going to put this in and do some tests and see what we can come up with. So I think somebody took a stab at fixing this, because there's a lot of parts that have been, looks like they've been removed and put back in or swapped. And it's all in this area here. All this, you can see all the solder joints that were done. Plus, somebody removed these power transistors. But yeah, it's a lot of stuff going on here. There's a lot of damage. Whatever happened caused a lot of damage. Okay, update time. So lots been going on here. What I did is I went through pretty much the entire amplifier. Oh, pretty much the entire amplifier on the one side. Even number parts is the side that had all the damage. Odd number parts, I'm assuming this amplifier is working. I'm going to leave it alone. I'm using it as a reference. So I've been poking around here and I don't see any bad parts on this side. But 17 components are either burned out, fried, out of tolerance, no good. So I got quite a list here of parts I'm replacing. I already started. So quite a few resistors open, blown up transistors. There's like 6 of them, and diodes, lots of diodes. For whatever reason, Technics uses these germanium diodes. There's one here, 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 here in the audio amplifier power section, and I think there's some kind of they're in with the biasing circuit. But there's 2 different types of diodes. There's the germanium ones, and then there's the stabistors. And I actually found some stabistors to replace the blown ones. Hopefully they're rated properly. Thermistors. They're temperature dependent resistors. There's 2 of them here. This one was cooked. It was totally wrong value. The schematic says they're supposed to be 10K. probably at room temperature. This one I think I measured at around 9. No, this one I measured at 10.5K. These thermistors are kind of rare birds, and there's marked 10K, and they have dots on them. There's a brown, black, orange, which signifies 10K to me. And I think this one measures 10.5K. This one, another one I found in my parts bin. It has 3 stripes on it, brown, black, orange, and I measured it's 9.5K. So I think it's close enough. I don't know how critical this value is, because it's going to change as temperature changes. Even if I heat them up with my fingers, it goes down to 7-8K. So I think they're just for tracking the temperature. Not sure how accurate it needs to be, but I did have one in stock, and I was happy I found it and popped it in there. So good. Got the caps changed. All the caps need to go because they are the Mashishita caps. Some of them are leaking. They have the green fuzz around one of the legs. And the problem with those caps, if you leave them in circuit and start using this amplifier on a regular basis, the heat cycles, the heat-cold cycles are going to start heating up, cooling off, heating up, cooling off. Those caps are going to start leaking down the leg, and it's going to cause a big mess. So you need to get them out now, even though this thing may not have been powered up in 20 years. So that's probably the reason why the caps aren't as bad looking as they should be. As soon as you put this back in service, it's all going to go to hell. So remove all those caps, replace them. Plus they are down in value. It's like, for example, a 10 microfarad would be down around 8.5 microfarad, and so on. So they're all going to get refreshed and replaced. And that includes some of these other boards like this one and this one. That's no problem. There's not that many caps in this thing. Now, my big dilemma right now is these germanium diodes. These germanium diodes are specified as a OA90. And I'm just trying to see the specs on this. And it says it's a 30 volt germanium diode. I'm trying to see here, 10 milliamps, you're going to have a 1 volt drop. So I could actually measure some diodes. I was more concerned about this, the 30 volts, because if it's this, we're going to have to find some high voltage germanium diodes, but I don't think we need those. The OE90 is a 30 volt diode from what I can tell, and that's puts my mind at ease. So I can pretty much dump anything in there as long as they're fairly matched together, and they as long as they're fairly matched together. So here's a look at all the damaged parts in this amplifier, and it goes way back up to this point. This stabilizer's gone, this transistor, and I still have to check some of these. I did a junction test on all these, and they were fine. I still need to check a few more. I want to make sure that this is all 100%. Plus, there's stuff on this side I can't see because it's cut off. There's a FET, a long tail pair, and all that stuff. I need to go and check all that, make sure that's good, because if we have a problem up front here, this will drive this into full conduction on one of the rails and blow everything up again. So, looks like it's going to be very doable. My plan is to replace all of these parts except the output drivers, the output devices. I'm going to power it up slowly and see if we have any problems in here. If everything seems okay, if everything's matching channel to channel, we can put our output devices in and then try it again, and we should have a functioning amplifier. Just want to make sure I get everything right here before I plug those devices in so I don't blow anything up again. Okay, so I selected these diodes here. These are, I don't know what they are. They read, I'll show you what they read. KS169, and then they have an 86. I don't know if that's a date code. L2, MI and a T symbol for IT&T maybe, I don't know. 752Y, lots of markings, but this KS169 doesn't cross-reference to anything I have. These are germanium diodes. Now, I was curious on their specs, so what I did is I made a little test rig here, a 10K resistor. Did some tests. I had forward current. I had the forward current jacked up to, I think it was 30 or 40 milliamps. And at that current, I was measuring about a 380 millivolt drop, junction drop, so it's a fairly stout diode. And I did reverse, powered this up with reverse with a power supply all the way up to 60 volts. At 60 volts, I was getting 11 microamps of leakage current, so that seems okay. So I think these diodes will work in place of this OA9, where I have a 30 volt peak reverse, 1 volt drop at 10 milliamps, 20 microamps at 10 volts reverse. I'm getting a lot better specs than this OA990. So I'm going to use these. I have about 40 or 50 of these. These are used pulls, but they're all good. I'm going to put these in the circuit, and we're going to go with that. So I removed the European cord, and that's going to go in the bin. I got a nice new polarized USA style plug, and we are going to install this now. I think this is probably going to be the most satisfying part of the job, is when you put a new power cord on and get to plug it in for the first time. And it hasn't seen power. It hasn't seen power in years. I know this thing sat here for. Actually, you know what? I got a special tool for this. Why am I fighting with it? I got a special pair of pliers just for these grommets. So I can squeeze it, push it in. Look at that. Just like I bought one. Okay. Now, here we have our little power input board. Got line and neutral, 2 chokes, a fuse. I upgraded this fuse from 2.5 amp to a 5 amp fuse, and I might change this to 4 amp. I'm not sure. We're going to see how it does on the full power tests, how much current it draws, and I want to have it fused properly, not just put anything in there. And then we got some capacitors to knock down an EFI. So we can connect our line cord up here, line and neutral, and I might redo this power switch, because the way it is now, they have both the line and the neutral switched, a switch on each, and I might remove that, put the switch on the hot side only, and I might double up the contacts on this switch so that it's going to handle the extra current. And then that would eliminate 2 wires running to the back, and we can clean up some of this extra wiring. So I'll do that right now, connect up the line cord, and probably reconfigure this. Alright, I think I'm ready to do my first power up. I got all the components replaced, and I don't think I missed any. I'm pretty sure I got them all. Computer board's back in, replaced all the caps in the unit. Things I pulled both relays and cleaned both of those, so they're good. We have no output devices. Okay, it's open, and we have our drivers installed, no outputs. And this is just a trial run, just to see if we have everything right in this area. Before I put the devices in, I want to try it. Another thing I'm going to do is I'm going to monitor the voltage across both rails with this meter. I'm monitoring the voltage drop across the resistor that is in between these 2 final drivers. If this meter goes high, then we know we got a high current or high voltage situation, and we might have done damage. Hopefully this stays low. I'm going to bring it up slowly on a variac and turn this thing on. Where's the power button? Right here. Okay. Variac's on. So let's bring this up. going to monitor current as I do this. Okay, so far so good. We've got nothing here, which is good. We're at plus and minus 20 volts. Keep going up. Thought I heard something. Relay click. Plus and minus 40 volts. Getting our lamps. I don't know if we have our computer starting up though. Alright, I think we're getting close to line voltage. We got half a volt or 600 millivolts. That's across a 330 ohm resistor, which is adequate, I think. It's less than a volt to drop. So I think our currents are all correct in our driver stages. I can actually do the math. Here we have I equals E over R. 0.6 divided by 330. So we're 1.8 milliamps. So we're all good. I'm kind of happy with this now. So I think what we should do is put the output devices in, add the heat sinking, and we can do our power up and do our first tests. I think this is going to work. So this amp came to me without any bracket here. This was missing. So the previous tech took it off, neglected to put it back. And here I am trying to figure out how to clamp these transistors down. Can't drill a hole because it goes right into the pipe. So I'm going to make a clamp, probably full width of this plate, have the 3 holes in it and the 2 locating pins, and then have it come down probably about halfway and clamp onto the center of the transistor. So I'll have to take some measurements and get that all straightened out before I go out and start cutting up some metal. Probably some 1/8 inch plate will probably work, and has to have a 90-degree bend, maybe 2 90-degree bends. I'm not sure. I'll have to look at this. Okay, just sizing up my options here for output devices. This is what I got in stock for 2SA1265s and 2SC3182s. So I got a mix of brand new and pulled devices. I went through and did some measurements on HFE, and the minimum HFE for the R rank is 55. So I got 2 transistors here that are below the minimum 55 HFE. So these are probably toast, these two. They still work, but they're probably toast, but we're going to eliminate those from the race. So I think I'm going to go with these 2 here. This is one that I pulled off the amplifier, and then I'll put one beside it, the opposite channel, and then I'll take these 2 here. The reason I'm picking low HFE is because if I blow these transistors up, it's really no loss. These are my brand new ones, and I'll leave those for other projects. And yeah, now I was thinking about doing something like this. I don't have to use these transistors. I can use pretty much anything. Do something like this, but there's just no room on here for 4 transistors of this size. This would be probably a smart upgrade considering the power we're going to be pushing with this now that we're with this amplifier. So I don't know, I didn't check the specs on these at all, but I just don't have room for 4 of those. They would be so tight together. So we're going to go with these 4, I think. Now, I did make up a bracket, a steel bracket out of like 3mm steel. I cut a couple of knobs on it and put some bends in it. I don't know if you can see the bends. Slight bend this way so it rests on the transistors. This goes into these two slots, and then our transistors go under and they get clamped down with the screw. Now if I clamp these down, I have to make sure that they are all clamped. This one's a little loose. I might have to shave a little off this one just so this one clamps better. Unless it will bend. But I'll just take a file and I'll just remove a little bit of metal here until it clamps better. Let's see how this goes. I'll take a little more. I'll adjust that after. But you get the idea. So 3 screws, clamps it down. I could even put something over top of the transistors, kind of rubbery like, to spread the force. Maybe I'll do that. I don't know if I have anything that I could put under here. But that's what it's going to look like, more or less. So let me get this this radiator installed and see if we can get this thing powered up today. Okay, we got our transistors bolted in. Everything went good. They're all secure. They're all clamped down. Just want to do our continuity checks because we don't want any shorts. So let me do that right now. Okay, so if we connect this here, everything's good. It's insulated. Alright, let's put it in the board. Alright, I think we're ready to do our first power on test. And I want to do is I want to feed a signal through the amplifier. I want to test controls to see if they're scratchy and if they're working. I have what I'm going to do is I'm going to feed it with 110 volts AC. So that should be the standard line voltage for this thing now that we rewound that. Now you got to remember, everything is experimental here. So when we put 125 volts onto this transformer, we're going to have elevated voltages on our caps, and I have a feeling it's going to exceed 63 volts, which means I'll have to replace these because they'll be over voltaged if I don't. So this is not monitoring line voltage, and everything's shut off right now. I don't know why it's reading almost 2 volts, but let's turn this thing on. It is on. Okay, and I'll turn on the power. I'm gonna ramp up the voltage slowly as I bring this thing up, and I got it feeding it a signal. So here we go. Usually when I get around 50 some volts, the relays start clicking in. We're not drawing any heavy currents. There's one relay. Oops. Let's do this without speakers. So we're up at 110 volts. Okay, let's check our outputs to see if we have DC, because it sounded like we had DC there for a second. We have lamps going on down here, signal. So what do we got here? Do we have any DC on this channel? Yeah, we got negative 54 volts, which isn't good. This channel, we got negative 47 volts. We've got big problems here on our amplifier. So we need to figure what's going on there. We're not drawing any current though. So I'm going to have to troubleshoot this with power on, just to see where our voltages are coming from. So we might have a bad transistor in there still in the front end, which yeah, we got negative 53.9, negative 47.9. Alright, so we still got work to do. Okay, I'm trying to figure this puzzle out here. I got DC on both outputs, which tells me something is wrong, not with one channel, but with both channels. Something that covers both channels. I checked out these FETs at the front end. They're all okay. I thought maybe I had a shorted FET, but no. Checked out 505 and 504. They're fine. And all of these transistors check fine. So then I'm looking at this DC servo amp right here. Now this thing is the amplifier before. If I follow the line, it goes into the main amplifier. So this is our last step before it goes out the door. Now I measure pin 4 and 8 and I have my plus and minus 21 volts. But I measured on pins 1, 2, and 3, 5, 6, and 7, and I had negative 21 volts on all of these, which was suspicious. There should be 0. So what I did is I unsoldered 2 and 3, which is the inputs, and 6 and 7, which is the inputs. And I still have voltage on, I think it is pin 3. I still have a voltage, and it's like 20 some volts. But I think this op amp is bad. This is a NJM 4560DX. I'm going to see if I have any of these. I'm going to pop a new one in if I can. I think this op amp is fried. That's what's giving me all these weird voltages. So let me see what I can do. So here's that op amp. It's located on the tone board next to the tone controls. And what I did is I desoldered pins 2 and 3 and 6 and 7. Those are the inputs. Now, they should be reading 0, and I power it up and I measure it, and we're measuring voltage on those 4 pins. Some of those pins, not all of them. So that what makes me think that this chip is fried. You know, with the inputs disconnected, I should get 0 on the outputs, and I'm still getting a voltage. So, yeah, we're going to replace that chip. All right, got the op amp replaced, and I did not solder the 2 inputs, or the 4 inputs on the two op amps. I left them unsoldered, so I just want to see if we still have our weird DC offset voltages. So let's power this thing up and see what happens here. Maybe it might come out of protect. It's still flashing. Okay. Let me check this. $41 volts. What the hell's going on here? Something is wrong. There's some really weird stuff going on here. All my voltages went wonky, and one of the rails jumped up high, the other rail is low. So I got connected to chassis. I got my negative lead. Let's turn this thing on. And this is, I don't know if you can see that. You can't see this. Let's put this in frame so you can see it, because this is important, I think. Okay, here's the voltmeter. I'm on DC volts. So here's one side of the capacitor. Oh, now it's going to play nice. Ah, now it's playing nice. This center point I had 20 volts between the two capacitors. This is our star ground, I believe. Oh, there we go. No, it's still reading 3/4 of a volt between chassis and here. So I got a high resistance ground. And I think it's this. Because I was poking at this. Now it's down to half a volt. This screw here is suspect. Just wondering if I tighten it down. Oh, it's loose. Okay. Let's see what effect that has. Turning it on. Drawing 21 watts. Let's check our ground. Okay, we have a good ground now. That loose screw threw me off on all my measurements on the other side. I was trying to track down. I thought it had open fuse resistor. It was just a nightmare. But it seems like I found the problem. So we had a loose screw. 55 volts on that cap. Negative 55 on that cap. I'm feeding it 105 volts. So we're not quite at full voltage yet. Now I need to go back here and troubleshoot this nonsense. I was having problems with this op amp. Okay, now my voltages have returned. Alright, so what do we got here? We got, I think we have a messed up op amp again. I'm measuring 20 volts all the way around. Yeah. So I'm going to have to order some op amps because that was my last one. And so I'm going to put this project on hold for a while until we get the parts in. I'm also going to order 2 new caps, 80 volt caps, because when I crank up the voltage to 125, this jumps up to about 65 volts on each cap, which is, I don't recommend overvoltaging electrolytics, especially when they're 40 years old. It just doesn't do anything for my warm fuzzy feelings. Okay, I've been bashing my brains out on this thing for the last few hours, trying to figure out what's going on with it. I have a feeling the amplifier is absolutely fine. It is working great. The problem is the DC servo at the beginning of the circuit. There is a DC servo in this circuit here, in the tone circuit, volume control, loudness, auto muting, balance, all these tone controls and circuits on the input of the amplifier. They have this op amp here, and it is a Japan Radio Corp. It's an NJM4560DX. Now they're feeding this op amp with plus and minus 22 volts. That's what's getting me. I can't get an op amp in that voltage range. These are plus and minus 18 volts, and these are 4560s. Not the same brand as the JRC. I don't know how they're doing it. I look at the JRC data sheet and it says plus and minus 18 volts, but they're feeding with plus and minus 22 volts. So I put a new op amp in, or actually first I get the power supplies working, the positive negative supplies for these op amps. They get it working. There was blown resistors and carnage. So I finally get it working. I get plus and minus 21.7, 21.4 volts working perfectly. I plug a new op amp in the circuit. Bang! It blows resistors, and it doesn't accept an op amp that doesn't have the correct voltage. So I'm at a pass here. What to do with this? I'm searching for an op amp that I can sub in that has a higher operating voltage. I think that's my solution. The other solution is I can modify the circuit to drop the voltage to those op amps down to something more reasonable, like about 5 volts, plus or minus 17 volts maybe. Yeah, so I'm at stumped with this right now. So I'm going to go do my search for another op-amp substitution. See, even the high voltage popped this Rubicon cap, brand new Rubicon cap, 25 volts. It just popped it. Here's the top. It's all domed out. The bottom, it blew its guts. So, yeah, this is frustrating, to say the least. Hey, welcome back. Why am I saying welcome back? Well, the last clip you saw was filmed in August of 2024. Now it's December. I got so frustrated with this thing, I just put it aside and forgot about it for a while. And the problem I was having is I couldn't get the amplifiers to properly balance. What I mean by that is the amplifiers were working. If I pulled out the op-amp chip that was in the beginning, if I show you here, there's a servo for the DC servo. If I pull this chip out, it would work, it would click in, the relay would click, and the amplifier was happy. But when I put the op-amp back in the socket for this DC servo, this DC servo is the beginning stages of this amplifier. And I would actually just remove it to get it to work, but I put the chip back in, it wouldn't work. It would have DC offset, 9 volts on the outputs. It would do really weird stuff. It would blow fuses, it would blow resistors, it would blow transistors. It was doing all kinds of nasty things. And I grew really frustrated with this. I was working on it and trying to figure it out, and nothing was working. So like I said, I put it aside and started working on other things. Today, I pull it out, and because I'm getting tired of stubbing my toes on this thing. It was sitting in my way, and there's parts of it laying all over my workshop here, and I just wanted to finish this and get it out of my hair. So today I put it on the bench. I got a free day. I'm going to work on it, and I start thinking about stuff here. Oops. Looking at the schematic first of all, there's many references to ground, and I'm thinking, well, I couldn't find a ground on this. So I got the ohm meter out and the continuity tester, and I started digging around looking for grounds, and there were no grounds in this part of the circuit. That's why it wasn't working. There was no ground reference here at all, and it was floating. It had plus and minus, I think the 21 volts is the supply voltage, and it was working that way without the ground. But I got to thinking there's got to be a ground here somewhere. So I started digging and digging, and I eventually found it. And it was actually on the input board. There was a screw terminal here that grounds a lot of the circuitry here in this thing. And if this screw is missing, this won't work. So what do? I attach a wire to the star ground, and it starts working. So I'm pleased. So this thing is actually, I had it fixed a long time ago, but this ground thing really threw me for a loop. So now I'm just doing assembly. I'm putting things back together. I put the heat sinks back on. I reinstalled some boards. I'm going to remove some bodges. There's some 100 picofarad caps here. I'm going to remove these and put chip capacitors, things like that. I'm going to clean this all up, get it working, and put it back together, and then we'll do our testing. That really relieves me, because I was starting to stress over this thing, and I really wanted to see it working. It's one of my pet projects, and you see, I put a lot of work into get it this far, and I didn't want to abandon the project at this stage. So this is good. So I'm going to continue putting things back together. I got a whole tray here full of dead parts that I've replaced over the last few months. And it's all got new caps. So this will be a nice amplifier once it's running. So let me finish, and then I'll bring you back in. We still have some more work to do though. Alright, like I said earlier, these caps, suddenly they're no good anymore. Well, they are good caps, actually. They're very good caps. But they won't work for what I want, because they're only 63 volts rated. And here we have, I measured 65 volts on both of these. So we have 130 volts across our B+. So yeah, you don't want to over voltage one of these caps, because it can fail catastrophically. So what I did is I went out and purchased these bad boys. Let's open this up and have a look. These are Nippon Chemcon. There's 80 volt, 22,000 microfarad, whereas these are 15,000. So a little boost in filtering. One issue we have is our pinouts. I'm going to have to cut off 2 of these. No, this isn't going to work at all. Negative. Oh yeah. I'll have to cut this pin off, and then the other pins will work on the holes. So this is what we're going with. And these are going to get set aside. Alright, got the new caps in, and we're going to do my first power up here. Actually it's the second, but we're not counting. So I got meters set up on the emitter resistors of both channels. This will monitor the bias current. This will monitor the power consumed. Here's the legend for the little lamp thing here. It says the 2 top lamps are your quiescent current for the idle. One's a preheat, one's an auto, and then we have 3 lights for bias. One's high, medium, and low. Okay, and then the bottom 2 are sensors, thermal and signal. So we have all these lights here, and you should see these lights come on and change as things get active. I'm going to plug this thing in, and we're going to power it up. I'm just going to monitor the bias for now. There is no adjustment for bias because it's all controlled by a computer chip. So here we go. Power on. And looks like it's doing the preheat thing. Now I'm just going to measure the center conductor of our emitter resistors just to see if we have any DC offset on the outputs. I don't think we do. I did not hear a click in the relay. That's concerning. Why is that? So let's try that again. This light's blinking. Still don't have any relay click. Let me check this. Still got 9 volts there. What the hell's with that? 9 volts on the outputs. That's why it's not clicking on. I did do some work on that backboard, and it looks like we don't have a ground anymore. Something's getting warm. I can smell something getting hot. Okay, I'm turning it off. Yeah, I had one connector unplugged. That's my fault. Now if this thing's still working, let's try it again. So here we go. This is our power consumption. Hope you can read that. Okay, switching it on. There's our click. And our lights. There we go. Looks like it's working. Okay, so we got, I'm measuring across both emitter resistors on these 2 meters. So we only have like 3.5 millivolts on this one, 1.5 millivolts on this one. So I'm going to measure again for DC offset, and it should be 0 now because it came out of Protect. Let's check this. Got 0 on that channel, 0 on both channels. Good news. Although it does, I do smell something getting hot. I'm wondering what that is. It's up at 40 watts now. And our bias light went out. We should have one of these 3 bias lights lit, but they're not lit. And this thing's climbing up in power. This side's climbing up in power, this side's not. Just going to let this monitor for a while and see what happens. It seems to be working. Watch the cycle as I shut it off and I restart. Watch the cycle of the lights and watch the meter and the power or the voltage on this meter here. So it's doing a preheat thing, and then the power will drop. It dropped from 51 to about 45. Now that's on this channel here, this one on this side. This one doesn't seem to be affected. This one seems to be lame. I don't know what's going on here, if I still have a problem on this channel with the biasing. This seems normal, I guess. Across both resistors, that's 15 millivolts across one. But this seems low. And we have our red light here, which tells us we're online. I'm thinking you might have a problem with the biasing on one channel. It's got these two bottom lights are lit. These is a thermal and this is a sensor or signal. Another thing is I haven't done any adjustments. There is adjustments back here for the automatic impedance detection circuit, speaker impedance detection circuit. So I think I need to go through and do a lot of that. But there is some kind of adjustment on this computer board. I don't know what it does. Looks like we're not out of the woods yet, so I'm going to keep plugging away with this and keep. I'm going to feed a signal through to see how it sounds. Okay, I don't really know what's going on with this bias, but it has a mind of its own. I think it's the computer taking control of it. If I turn up the volume, we have audio both channels. It sounds good and clean. Watch the bias. Both the same. If I turn it down. So something to do with the volume of the signal going through. Yeah. Now, I did clean the two switches in the back, this one and this one. This is a function switch, input select, and this one's record select. This is your speaker switch. I didn't touch this one. I cleaned the moving magnet, moving coil switch, but these three down pretty crunchy, these three here. I might just remove these three and clean those. This is our balance control. It's dirty as well. Okay, so now I have a good idea of what more I need to do. Balance control, these three switches, clean the volume pot, and do an alignment on this. Okay, a few notes on servicing. What they're saying here is, number one, before you do any work on this amplifier, you want to drain the bulk filter caps 403, 404, and 405. These are the main filter caps for the unit, and you use a 10 ohm resistor 5 watt and discharge the capacitors. It says do not short between C403, 404, and 405 with a screwdriver. You don't ever want to do that on these big bulk capacitors. You don't want to short them out because they have a hell of a wallop of energy inside them. And not only are you going to damage your screwdriver, but you can damage the cap and you can damage the traces on the board and everything. Now, next, they talk about before turning on the power supply after completion of the repair, slowly apply a primary voltage using a power supply voltage controller, like a variac, to bring it up slow, to make sure that the consumed current is free of abnormality. Okay, and what they're talking about is don't just plug it in like I do and power it up. They want you to bring it up slowly. And then it says consume current at 50-60 hertz and no signal mode is shown below with respect to supply voltage. So depending on where you are in the world and what frequency you're feeding it, this should be your line consumption current. And for hours, we took an AC220 and converted it to 210 or 110, sorry, at 60 hertz. So you can safely double these two numbers, 100 and 320, to 200 and 640 milliamps, and that should be your guide as to what the current consumption should fall into. Now you can look at the other ones, 180 to 570 over here. It's getting kind of close to our 640, 570, yeah. But let's look at what we have now. So when I turn this thing on, our current consumption up in the left, in the middle there, shows 480 milliamps. Relay clicks in, it drops to 370 and comes back up to 460, and it kind of sits there now. So we're within the limits of what they're asking, and we'll just leave it at that for now because we haven't adjusted the bias. We're going to do that next. Now this might be a little hard to read. My apologies. It was grainy print on this manual. So first, for setting up, we need to set the clock, the microprocessor clock. And what they're doing is turn off power supply, adjust VR501 so that the time of the relay turns on is 5 to 7 seconds after power on. Now, what they're doing there is they're setting the microprocessor clock frequency to a time so that it takes 5 to 7 seconds to this thing to wake up. The time elongates with VR501 turned counterclockwise in the direction of A. Frequency decreases. Time shortens with 501 turned clockwise, direction of B. Frequency increases. Clock frequency of 400 kilohertz is obtained at test point 501. In the case of ordinary frequency counter and oscilloscope, the frequency cannot be correctly measured because of the probe capacity, so it's recommended to employ the above method. So they want you to use the time method rather than the frequency method. But there's a way around that. I'll show you. So here's your computer board over here, and here's your microprocessors on here. Here's VR501. So if you turn it, A is counterclockwise, B is clockwise. Here's the capacitor. There's a ceramic capacitor I'll show you here. Here's the ceramic capacitor, and here's the trim pot. Okay. You can take a measurement off of this pin, test point 501, and what you do is you tack on a 100 picofarad capacitor to this lead of the cap, and then you can attach your frequency counter to it, and you can measure the frequency. That's what I did. 100 picofarad tacked on, connected frequency counter, adjust this to 400 kilohertz. Okay, it's pretty simple. And if you get it wrong, big deal. All it does is it sets up the frequency for this computer chip and how fast it runs. If you turn it too slow, it's going to wake up slower. If you turn it fast, it's going to go faster. Okay, so idling current adjustment after repairing the main amp. So what they want you to do is nothing on the speakers, turn the volume down, turn the ICQ controls BR301 and 302 counterclockwise to decrease the bias current completely. Then they want you to do the input line power current test that I talked about earlier, just to make sure that it's below the value that's specified in the manual, just to make sure you don't have a damaged amplifier that's drawing excessive current. Then you connect DC electronic voltmeter to test point 302, 301, 304, and 303, and that is on the emitter resistors. Okay, that's on the outside connectors, the outside conductors of both emitter resistors. Here's one shown, the other one you can't see. So just like that, connect your voltmeter up. What they do is they want you to turn on the power and wait 5 to 15 seconds until the computer drive monitor goes into the auto position. So there's a preheat time. When you first turn it on, there's a preheat. You don't want to do any adjustments during this preheat. You want to wait till it switches to the auto, and then it starts doing its slow climb. This is where you want to do your setting, right after it drops, after it switches into auto. And then from there you set your left and right channel to 2 millivolts on your voltmeters. Okay, you only got so much time to do this. You can't turn this on and wait 5 minutes and then adjust it, because this will be doing its slow climb already. So once it switches from preheat to auto, Then you make your adjustments for 2 millivolts, and then you set it, and you're done. Okay, volume's turned down, speakers shut off. Let's turn the power on. Wait for it to go from into auto. Once this lights up, there we go. Now we can start making our adjustments. Now these are both in millivolts. Let's do this one first. This is VR301. Which one is that? Okay, so we need 2 millivolts here. Okay, the other one, the other channel. Two millivolts. Okay, I'll leave that at that. And it's going to climb up. Now the computer is in control of the bias. This is what they tell me. This is what I'm led to believe, so I'm going to leave it at that. It's not quite exactly matched, but close enough. Alright, so we're going to adjust the load impedance detection circuit, which is going to sense the speaker impedance when you first switch it on. Now, what they want you to do is get a 6.5 ohm resistor, 2 of them, one for each channel, and put them on the speaker terminals. Okay, it doesn't have to be a big heavy resistor, just a half watt. And then you need to connect to your voltmeters. There's 2 voltmeters, one for each channel. One to test point 701, which is up here on this board beside the relay. Okay, this red wire. And test point 702, which is for some odd reason back here on this board, hidden behind the heatsink and the trim pots. So that's the other meter. No, that's this meter. This is the first one. This is 701, this is 702. Get that straight. Now we also take a clip lead and we ground test point 601, which is right here next to this connector on this top board here, this speaker board, and we have to ground this. So we'll connect that as ground, and then I think we just turn it on and watch the sparks. No? Don't do anything. Turn it on, and then we have to adjust these for 200 millivolts. We do 701 first. Well, that ain't right. That ain't right. What's not right here? Disconnect this ground wire. Ah. Let's try that again. We have, let's see here. We have our resistors in place, our voltmeters. Turning it on, we should get 200 millivolts. Why did we got 10 volts on this one? That's really odd. Let me adjust this one here. Yeah, that's not right. Let me turn this one down. Negative. Okay, I think I see what's going on here. That's 400. Volts. It's not a very good adjustment. 200 millivolts there. This one. $200 millivolts there is very touchy. There's 200 millivolts on that one. Looks like there's some interplay between the two of them, so you have to get them both. down around where they should be. But it said negative 200 millivolts. That's what it said on the sheet. I can't read it. It's very poor print quality, but it says 200 millivolts. Negative 200 millivolts. I'm assuming. So let's see if we can get that. We've got positive millivolts here. Let's try this one some more. See if we can get into the negative region. There we go. Okay, it's 220 negative. Let's try this one. There we go. 180. This one jumped. These meters should be this way, because this is left and this is right. Okay, that's what's confusing me here. 701 is left, so let's adjust 701 to negative 200. See if I can get this close. It's very touchy. 191, okay. VR 702, we got 1.4. Let's turn this down. This is really tough. Hang on. I treated these pots too so that they'd be bad. They're not twitchy, they're just really sensitive. There it goes. Get it down a little more. What happened? Took my screwdriver away in it. Let's see if we can get this here. 186 millivolts. It sure is moving around a lot. This trim pot is okay. Let's try adjusting this again. There. See, it is jumpy. This channel's stable, but this one isn't. Let's turn this off. Let's try it out. Well, I don't know if that is on the 8 ohm or 4 ohm, because the only way to really tell is measure the voltage across your filter caps. And if they have the high voltage or the low voltage, then you know which mode it's in. Because the relay click, I didn't hear a relay click, and it might have clicked the same time as the other one, I'm not sure. But yeah, it is what it is. So, and you know what? If the circuit doesn't work, I really couldn't care less, because I don't use 4 ohm speakers. I always use 8s. So to me, I'd rather just have it stuck in the high wired mode. Okay, here's a test of the impedance detecting circuit. I'm just going to connect the voltmeter here across one of the caps. If I can hold this steady with one hand, I can flip this power switch with the other. Okay, I think we're there. Can you see that? Let me check. Yeah, you should be able to see that. Okay, turning power on. And watch, it goes up to 65 volts. Relay clicks, drops back down to 52. It appears to be working. Let's turn speakers off. And we'll try that one more time. Turning it on. Stays at 65. The speaker shut off. Okay, I think it's working. Because my bench speakers I salvaged out of a plasma TV. A couple of big speakers. I don't know if they're 4 ohms. They might be 4 ohms, for all I know. Okay, let's do power test. I've been actually doing frequency response and distortion tests. And it's flat as a ruler up until about 30 kilohertz. Then it drops half a decibel. Distortion not so good. I was getting 0.04% on the right channel, and then I put the lid on and that dropped to 0.02%. So I think my distortion readings are fuzzed up with noise, and I think they're not accurate. The reason behind doing all this fancy schmancy pants computer bias control is to get distortion low on the amplifier. And I'll put it up on the screen and let you read it. There's an explanation on how this all works, and the bias is controlled by the computer according to a few things. I didn't really read through it. I couldn't be bothered. I'm not interested. Okay, I think for this I'm going to remove the lid just to let the heat out. And let's get this thing going. This thing's actually getting quite warm already, and it's only consuming 72 watts. I'm wondering what that's all about. Alright, let's go up in amplitude and check for clipping. Let me adjust this. Oh, and that didn't happen. What did we blow up? I think we lost the channel, didn't we? Let me turn this thing down. You get no clicky clicky. So, where's our fault? So that channel blew up. We got 65 volts on the output. This channel is still working. So we had one channel give up. Don't know why. Okay, let's shut this down. Well, here we go. Here's a look at the damage. We got both output devices are gone. We have the NPN driver gone, the NPN pre-driver gone, a 330 ohm resistor gone, a stabilizer which has a 600 millivolt voltage drop across it now. I happen to think one of the internal diodes is shorted. 2 germanium diodes gone. So there's a lot of damage on this one channel. Now, before it blew up, I noticed it was actually heating quite a bit, and quite a bit of heat coming out the radiator. I didn't pay any attention to it. I thought it was something normal, that because I was doing tests at 1 watt per channel, and I didn't think anything was wrong. I just thought it was consuming a lot of current. Now, It's kind of suspicious that this was on the same side that was damaged before, and I'm beginning to suspect that maybe there's a problem with the computer drive, the computer biasing circuits went into an overconduction situation, and too much current was dumping through these two transistors, which caused them to fail, which then caused a chain reaction going back. So I hope that's not the case. I'm going to repopulate these with new devices, and I'm going to put it back on the bench, and we're going to try it again. This time we're going to connect some monitoring equipment to the bias of both channels, and we're going to watch it as we do our power test this time. I was ramping it up. I didn't even see the numbers of how far I got, but it was something around I don't know. I couldn't comment on how much power this thing was putting out when it blew up, but it was obviously overheated. So let me repopulate those parts, and we'll try again. All right, got some new silicon in the amplifier. Replaced the blown resistors. Everything's back to normal. I powered this up on a Variac, and it comes out of Protect, so no more short circuits. So let's turn this on. I'm going to monitor the bias here for a while and see what goes on. If this thing flies or fries, I don't know. So here we go. Came out of Protect. It's on preheat, but we have no millivolts. As soon as it comes out of preheat, there it goes. So this should rise up to, what was it again? I think it was, after 20 minutes, they're saying 20 millivolts. So let's see how this little curve here goes. I'm just going to monitor the voltmeters and see how this goes. It's already up at 3. Okay, this has been on for about 20 minutes now, and it's stable at 16 millivolts each channel. Now when I first turned it on, this one rose up to about 15 or 16 and stayed there. This is the channel that blew up last time. This is the channel that didn't blow up. It went up to about 32, and it kind of hovered around 25, 26. So I turned this channel back down to match this channel. Now I did some tests within the ICQ circuit. There's two transistors, Q329 and Q330. They take the signal from the microprocessor, and then they translate it into the bias circuit. And I tested voltages on both these transistors. They're both equal within, you know, a millivolt or 2 millivolts. And I don't see any discrepancies between the two channels. So there was no reason other than a bad adjustment for this to skyrocket up twice of what this was. But I got it back down again. It's sitting here stable. It's not doing anything. It's sitting idling. And the radiators are getting slightly warm. I took my heat camera and looked around, and I didn't see anything bad. You know, I gotta say, this thing's ready for prime time. But let's try another power test. I want to see how this thing delivers full power. That's what I really want to do. So I'm going to shut this off. We're going to connect it up all our gear. And for whatever reason we blew up the amplifier last time, we're going to try not to do that again. So let me get everything connected and I'll bring you back in. Okay, take 2. Let's turn this on. Let's get this done before it blows up again. So I got voltmeters monitoring bias current, both channels. Here's our total power consumption. I got a signal going in. Let's turn the signal on. There we go. Okay. Now let's turn speakers on. There, click. All right. I think we're live. Let's go. Let's turn this up. Quite a bit of. This is what I don't understand. Oh, I'm at 15 volts already. Okay, let's keep going. If we blow it up, we blow it up. What is clipping? Actually, let's do this better. Let's get some more resolution on this. Okay, I just want to turn this one down a bit and then turn this one up a bit. Just so there. Okay. Let's figure out where our point is. Right there. Alright. That is full power. We've got 500 watts going in. We've got 30.56 volts RMS on the output. That's quite a high flyer there. Let's see how long this lasts. 32.09 on the right channel. That's close to 130 watts a channel. That thing's really smoking. Those little transistors. Okay, we're at the 9-minute mark here, and I've just been taking some measurements of temperature. Heat sink is well over 80 degrees Celsius. Down here we're measuring closer to 100 around those transistors. This side here, the radiator is sitting at about 70 degrees. This side here is quite a bit more. Let me see if I can get it more. Yeah, this thing's over 200. This is doing really good considering it's pumping out about close to 130 watts a channel. This amplifier is only rated for 90 watts a channel, so it's got a little boost to it. But I'm going to take this down here. I'm going to shut this down. Oh, one more thing I want to talk about is this little noise going on here and here, here and here. It's in the right channel only. If I turn it down, it disappears completely. It only seems to happen right at the very maximum power. It's a little bit of a spurious oscillation there. Yeah, I'm pleased. This heated the room up pretty good. Survived the 10-minute torture test at full power. This thing is really cooking. 90 degrees. So I'll let this cool down and we'll wrap it up from there. I think I'm done. I'm done working on this thing. I've seen enough of it for a lifetime. I'm kind of interested to see how well it sounds. So we're going to do that after I get it finished. So let me clean up here and then I'll bring you back in. Well, let's do one thing before I disconnect everything. Let's take a look at some square waves. So I got 1000 hertz tone. Let's let me turn down the scope on this. So we don't need full power for this. We're just going to go up a little bit. So there's 1000 hertz tone. It looks very, very good. And let's see here. Tone controls are out right now. Tone controls in. Bass cut. Bass boost. That's pretty good. Treble cut. Still a little scratchy. Treble boost. Yeah, we gotta work on these controls more. Okay. Now let's go up in frequency. We're probably at about 1 watt output right now, so let's go 2, 3, 4, 5 kilohertz. 6, 7, 8, 9, 10 kilohertz. 11, 12, 13, 14. 20 kilohertz. It's looking pretty good. This is a fast amp. We lose our square wave right around here somewhere. This is 41 kilohertz. It's pretty good. Looks pretty good. One of the better ones I've seen. Okay, well here's a look at the parts that are replaced. These are the original bad parts that came in the amplifier when I got my hands on it. I got a thermistor, a couple dead transistors here, they blew it up. A couple more, a lot of dead germanium diodes, a few fusible resistors missing, and a couple of lamps. And then this is what blew up. This is what I blew up yesterday when I was doing the power test, or started to do a power test, I guess. I have a feeling this thermistor diode was bad and I didn't catch it, and that caused a cascading effect of crashing everything here. 4 transistors, 2 diodes, 3 diodes, and a 330 ohm resistor. So those are the parts that blew up the second time. Last thing I need to do is apply a sticker. So I'm going to apply this in the back. I'm kind of pleased about this conversion. It not only did it brought the amp back to life, but it gave it fresh new power that you can't find otherwise. Oh, I'm putting it on crooked. I don't want crooked. It's got to be straight. Ah, there we go. So hopefully this will make somebody happy, this amplifier. There it is, it's done. I'm going to enjoy listening to this one for a while, see how it sounds. It's got some nice features too. It's got 2 tape loops, tuner, auxiliary, moving magnet, moving coil, tone control cutouts, 2 sets of speakers, 2 dubbing loops. Yeah, this is a good one. I'm going to post this December 20th, so this will probably be the last video you see before Christmas. So Merry Christmas to everybody. Hope you're all well and enjoy the season. So take care, and we'll see you. Thanks for watching.